Greetings of the day. Today we will be discussing about assignment 1 of heat transfer, which will be presented by me. My name is STEFAN-BOLTZMANN. My roll number is 191120103. I am currently in chemical engineering 2019 batch and I am studying Dr. B.R. Ambedkar National Institute of Technology, Jalandhar. So, the topic given to me is radiation heat transfer. Now, radiation heat transfer, as we all know, is a very vast term which covers a lot of topics. In today's presentation, we will be discussing these topics very briefly so that we can get a brief overview of what radiation heat transfer is. From this animated image, we get a brief idea of what we are going to discuss in this presentation. So let's get started. So let's first get a brief overview of the topics we will be discussing later in the presentation through a small index. So the first thing we will be discussing is the introduction. Now this introduction will cover the definition of the radiation, the factors on which it is dependent, and the emission process. The second one will be about the electromagnetic spectrum, in which we will be seeing the spectrum which emits the thermal radiation, and we will be discussing quite a bit about that. And then an important topic will be the black body, in which we will be discussing about what a black body is and what are its properties. Then we will be discussing about some important terms which will be used in this whole presentation quite a few times, which are absorptivity, transmissivity, reflectivity, and emissivity. After that, the next topic would be the grey body, and after that we will be discussing about specular body and absolutely white body. After that, transparent body, or we can say diatherminous. After getting a brief idea about the grey body, specular or absolutely white body, and transparent body, we will be moving towards the main topic of the presentation, which will be the radiation laws. Now in these radiation laws, we will be discussing about STEFAN-BOLTZMANN law, Planck's law, WIEN'S law, and KIRCHHOFF'S law. Now these laws are very important as far as the topic is concerned. We will also be driving these laws and see how these laws are connected with each other. The next important topic will be emissivity, in which we will be discussing about the definition and the equation of emissivity. After that, we will move on to the emissive power, which is again an important topic, and then gradually we will move to heat transfer rate by radiation, in which we will be discussing the rate of heat which is transferred by the radiation. After that, we will move to a very important topic, which is the view factor and how it is derived. Next, we will see some properties of the view factor, which will be very important in its derivation, and they are reciprocity rule, superposition rule, symmetry rule, and summation rule. The next important topic which we will be discussing after the view factor is the heat exchange between non-black bodies, under which we will discuss the heat exchange between two infinite parallel planes. The next topic, which will bring us to the end of the chapter, will be the interchange factor. We will be discussing just a brief overview of what the interchange factor is. So let's get started with our presentation. So let's start with introduction. So what is radiation? Radiation is the emission or transmission of energy in the form of waves or particles through space or through a material medium. So what is thermal energy? Thermal energy is the electromagnetic radiation emitted by a body as a result of its temperature. There are many types of electromagnetic radiations and thermal is one of them. The wavelength of these thermal radiations lies in the range of 0.1 to 100 micrometer, whereas visible light has wavelength from 0.4 to 0.7 micrometers. Now question arises, what kind of matter will emit electromagnetic radiations? So the answer is any matter with temperature above absolute zero, that is 0 Kelvin, will emit electromagnetic radiations. If we put it simply, radiation comes from the constantly changing electromagnetic fields of the oscillating atoms. These electromagnetic radiations can be visualized as waves which are traveling at the speed of light. Now the two prominent characters of the wave are its wavelength and their frequency. So what is wavelength? Wavelength is the distance between crest to crest on the wave, or we can also say it's a distance between trough to trough on the wave. Whereas frequency can be defined as the number of waves which pass through a particular point in a particular time. Now this frequency is related to wavelength by the following equation, which is mu is equal to c by lambda. Mu here is defined as frequency, c is the speed of light, and lambda is a term for wavelength. Now the amount of radiation emitted by a body depends on its temperature and is proportional to T raised to power 4, where T represents temperature of the body. This relation shows us that as the temperature of the body or the object increases, the amount of radiation emitted by the body increases very rapidly. The emitted radiations will travel at the speed of light until it is absorbed by another body. This absorbing medium can be gas, liquid, or any other solid. Also, radiation does not require a medium to pass through. Now this is demonstrated by solar radiations, which pass through interplanetary space to reach us on Earth. Moving on, we have the emission process or the radiation phenomena. For gases and semi-transparent solids, emission is a volumetric phenomenon. That is, the radiation through these is a volumetric phenomenon. This is perfectly represented in this diagram. However, in most solids and liquids, the radiation emitted from interior molecules is strongly absorbed by adjoining molecules. Only the surface molecules can emit radiation. Therefore, for an opaque, that is a non-transparent matter, radiation is considered as a surface phenomena, since the radiation emitted by the interior regions of the matter can never reach the surface. This can also be perfectly represented by the following diagram. Next, we will see the representation of emission of a hemispherical surface. Now, we have a diagram which represents a hemispherical surface, and we have a ray vector through the center of the hemisphere, which is making angle theta and phi with the respective perpendicular axes. Next, we see how the rays are spread in different directions as shown in the diagram. So, the emissive intensity of this radiation can be seen by this equation. IB is equal to EB by pi, which in turn is equal to sigma T raised to power 4 pi pi. Here EB stands for emissivity, and T, as told before, is the temperature of the body. Sigma is the STEFAN-BOLTZMANN constant. Also, the radiation emitted by a body is spatially distributed. That is, IB is a function of R, theta and phi. Next, we have electromagnetic spectrum. Now, in the diagram, we see a band of electromagnetic radiations which is classified into gamma rays, X-ray, ultraviolet, visible light, infrared red rays, microwaves and radio waves. Electromagnetic radiation is categorized into these types by their wavelengths. The type of radiation and the respective wavelength ranges are shown in the figure. The radiation with shorter wavelength are more energetic, which is also evident by the harmful nature of gamma and X-rays on the shorter end of the spectrum. Radio waves, which are used to carry radio and TV signals, are therefore much less energetic. However, they can pass through walls with no difficulty due to their longer wavelengths. The type of radiation emitted by a body depends on its temperature. In general, the hotter the object is, the shorter the wavelength of the emitted radiation and the greater the amount. A much hotter body, such as the Sun, which has a temperature of approximately 5800 kelvins, emit the most radiation in the visible region. So, as far as the thermal radiations are concerned, the thermal radiation include visible and infrared regions and also a part of ultraviolet region. Moving on to a very important topic, that is black body. Now, this black body is just a theoretical concept. That is, it's not possible to make a black body practically. The characteristics of a black body are that it is a perfect emitter. At any prescribed temperature, it has the highest monochromatic emissive power at all wavelengths. Also, a black body absorbs all the incident energy, and therefore alpha is equal to alpha lambda is equal to 1, which simply means that it is a perfect absorber. Also, it is a non-reflective body, that is rho is equal to 0. It is also opaque, that is tau is equal to 0. Now we will be discussing about this alpha, rho and tau and what they are later in the presentation. Also, it is a diffuse emitter, that is it emits radiation uniformly in all directions, that is there is no directional distribution. Next, we will be studying about some important terms which are very important to learn if we want to study radiation heat transfer. The first term which we are going to study is absorptivity, which is represented by the symbol alpha and is defined as the fraction of incident energy that is absorbed by the object. Next, we have transmissivity, which is represented by the symbol tau and is defined as the fraction of incident radiations that is transmitted through the object. After that, we have reflectivity, which is represented by rho and is defined as the fraction of incident energy that is reflected by the object. Also, we have a very important relation between absorptivity, transmissivity and reflectivity, which is the summation of all of them, that is alpha, tau and rho should always be equal to 1. Next, we have emissivity, which is represented by epsilon and is defined as the ratio of the emissive power of the real body E to the black body. It can also be represented as epsilon is equal to E by EB. E here represent emissive power of the real body, whereas EB represented emissive power of the black body. Also, we can get a brief idea of what all of these terms mean from this diagram. Now, let us consider any body such that total incident radiation on the body is absorbed, partly reflected, and partly emitted. According to the nature of the body, it can be classified into 4 types, namely opaque body, which has tau, that is transmissivity, equal to 0, and the summation of absorptivity and reflectivity, that is alpha and rho, is equal to 1. Next we have black body. As discussed earlier, it has alpha equal to 1, tau equal to 0, and rho equal to 0. Next in the line we have white body. White body have rho equal to 1, that is they are perfect reflectors, but they have alpha is equal to 0 and tau is equal to 0. Next we have transparent bodies. Now, as the name suggests, tau should be equal to 1, alpha equal to 0, and rho should be equal to 0. Moving on, we have an important note which says, in general, these physical properties, that is emissivity, transmissivity, absorptivity, and reflectivity, vary with the wavelength of the incident radiation, that is, they are the function of wavelength. For heat transfer calculations, we often assume that the properties, that is alpha, tau, and rho, are independent of wavelength, and when this assumption is made, we say that we have gray surfaces. Now, what is a gray body? A gray body has absorptivity less than unity, that is alpha is less than 1. Also, absorptivity remains constant over the range of temperature and wavelength of the incident radiation. For a real body, it does not satisfy the condition of constant, so gray body is a concept only, similar to the black body. Next we have specular body and absolutely white body. A body that reflects all the incident thermal radiations is called a specular body if reflection is regular, that is, it is a perfect emitter, or an absolutely white body if the reflection is diffused. For such bodies, rho is equal to 1, alpha is equal to 0, and tau is always equal to 0. Next we have reflections. Here we have 2 diagrams which will help us understand the difference between the specular and the diffuse reflections. The first one we see is a specular reflection. Here we can see that the angle between the incident and the normal is equal to the angle between the reflected ray and the normal, whereas in diffuse reflection we see the angle of incident is never equal to angle of reflection. Next we have transparent or diatherminious bodies. It is defined as a body that allows all the incident radiations to pass through it is called a transparent or diatherminious. For such bodies, we have rho and alpha equal to 0, but tau is equal to 1. Transmissivity varies with the wavelength of the incident radiation. A material may be transparent for certain wavelength and non-transparent for other wavelengths because it's a function of wavelength of the incident radiation. A thin glass plate transmits most of the thermal radiation from sun but absorbs in equal great measures the thermal radiation emitted from the low temperature interiors of the building. Now this can be considered as an example of the upper treatment. Next we have a very important concept of black body radiation. Now the energy emitted by a black surface varies with number 1 wavelength, number 2 temperature, and finally number 3 surface characteristics of a body. For a given wavelength, the body radiates more energy at elevated temperature, that is at higher temperatures. Next we have radiation laws. Now again, it's a very important topic in radiation heat transfer. The average of or bulk properties of electromagnetic radiation interacting with matter are systemized in a simplest set of rules called the radiation laws. These laws apply when the radiating body is what physicists call a blackbody radiator. Generally, blackbody conditions apply when the radiator has very weak interaction with the surrounding environment and can be considered to be in a stage of equilibrium. Although stars do not satisfy perfectly the conditions to be a blackbody radiators, they do a sufficiently good approximation that is useful to view stars as approximate blackbody radiators. Next, we will discuss about the radiation law for blackbody radiations. Under this, we will be studying STEFAN-BOLTZMANN law, Planck's law, WIEN'S law, and KIRCHHOFF'S law. So let's get started. The first one we have STEFAN-BOLTZMANN law, and it states that the total emissive power E of a surface is defined as total radiant energy emitted by the surface in all directions over the entire wavelength range per unit surface area per unit time. The amount of radiant energy emitted per unit time from unit area of black surface is proportional to the fourth power of its absolute temperature, as we have discussed previously in the presentation. Mathematically, it can be defined as EB is equal to sigma B multiplied by T raised to power 4, and its units are given as watt per meter square, where EB is called the blackbody emissive power, EB is the radiation coefficient of blackbody, also called as STEFAN-BOLTZMANN coefficient, and its value is 5.67 into 10 raised to power minus 8, and its unit is watt per meter square Kelvin square. And lastly, T is the absolute temperature of the surface and is measured in kelvins. Now let us derive STEFAN-BOLTZMANN law. Now it can be written as EB is equal to integration 0 to alpha E lambda B d lambda, which can be rearranged in terms of C1 and C2 as integration 0 to alpha C1 lambda raised to power minus 5 divided by exponential C2 by lambda T raised to power minus 1 d lambda. Now letting y equal to C2 by lambda T, we have d lambda, which is equal to negative C2 divided by y square by T multiplied by dy. And as lambda reaches 0, we can see y reaches alpha, and similarly as lambda reaches alpha, y reaches 0. Next, applying the above changes, we have EB, which is equal to minus C1 integration alpha to 0 y raised to power 5 t raised to power 5 C2 divided by C2 raised to power 5 multiplied by exponential y minus 1 multiplied by y square into t all multiplied by d lambda. Now we know C1, C2 and T are constants, so we take them out of the integration and we are left with integration, and we are left with y cube multiplied by exponential phi minus 1 raised to power minus 1 multiplied by dy and the integration. Next, using binomial distribution, we change the term inside the integration to y cube into a series of exponential with the minus y as a arithmetic mean, and we do so by expanding exponential y minus 1 raised to power 1 by binomial distribution. Next, we have integration 0 to alpha y raised to power 1 exponential minus alpha y multiplied by dy, and this is always equal to factorial n divided by alpha raised to power n minus 1. Using this expression in the previous equation, we get EB, which is equal to C1 t raised to power 4 divided by C2 raised to power 4, and this whole term is multiplied by a series of 3 factorial divided by 1 raised to power 4 plus 3 factorial divided by 2 raised to power 4, and so on up to infinity according to the above expression. We get C1 t raised to power 4 divided by C2 raised to power 4 into 6.48 after solving the equation in the bracket, and after putting the values of C1 and C2 we get the required expression of STEFAN-BOLTZMANN law, which can be defined as EB is equal to sigma b t raised to power 4, where comparing both the equation we get sigma b is equal to 5.67 into 10 raised to power 8 watt per meter square Kelvin square, which is also called STEFAN-BOLTZMANN constant. Now, if there are two bodies, the net radiant heat flux will be given by Q net should be equal to sigma b multiplied by the difference of the fourth power of the temperature of the respective bodies. Now let's move on to the next law, which is Planck's distribution law. The primary law governing black body radiation is the Planck's radiation law. This law governs the intensity of radiation emitted by unit surface area into a fixed direction, that is solid angle, from the black body as a function of wavelength for a fixed temperature. The Planck's law can be expressed through the following equation, which is EB lambda T is equal to 2 pi hc square by lambda raised to power 5 multiplied by E raised to power hc by lambda kt minus 1, and its unit is watt per meter square micrometer, where h is equal to 6.625 into 10 raised to power minus 27 erg per second, and is also called as Planck's constant. K is 1.38 into 10 raised to power minus 16 erg per Kelvin, and it is also known as Boltzmann constant. C, as we all know, is the speed of light in vacuum, and lastly lambda is the wavelength of the radiation waves, and it is measured in meters. And lastly we have T, which is the absolute temperature of the black body and is measured in Kelvin. Next, we have Planck's distribution law, can also be expressed as EBT is equal to C1 divided by lambda raised to power 5 E raised to power C2 lambda T minus 1. Now this is just a simplification of the previous equation by just rearranging the equations and putting 2 pi hc square as C1, whose value is 3.742 into 10 raised to power minus 8 watt micrometer raised to power 4 by meter square and putting Hc by K equal to C, whose value is 1.4389 into 10 raised to power 4 micrometer Kelvin. We should note that this equation is for a surface in a vacuum or a gas. For other media, we can replace C1 with C1 by n square, where n is the index of diffraction of the medium. Now integrating this function over all lambda will give us the equation for EB. That is, EBT will be equal to integration of 0 to infinity EB lambda t multiplied by t lambda, and it will give us sigma t raised to power 4, which is none other than our STEFAN-BOLTZMANN law. Next, we will be discussing about spectral energy distribution. Now, we know EB lambda denotes monochromatic, that is single wavelength emissive power, and is defined as energy emitted by the black surface in all directions at a given wavelength per unit wavelength in interval around lambda. The rate of energy emission in the interval d lambda is equal to E lambda b multiplied by d lambda. The variation of distribution of monochromatic emission power with wavelength is called as spectral energy distribution. Now that we have got an idea of what spectral energy distribution is, let's visualize it through a graph. So the behavior is illustrated in the figure. The Planck's law gives us a distribution that peaks at a certain wavelength. The peak shifts to shorter wavelength for higher temperature, as you can see in the graph. Also, the area under the curve grows rapidly with increase in temperature. This is because it is proportional to the temperature. So we can check these points in the graph also. Next, we have monochromatic emissive power, which is denoted by EL. All surfaces emit radiation in many wavelengths, and some, including black bodies, over all wavelengths. The monochromatic emissive power is defined by dE, which is equal to emissive power in the wave band in the infinitesimal wave band between lambda and lambda plus d lambda. That is, dE is equal to E, which is a function of lambda and temperature, multiplied by d lambda. The monochromatic emissive power of a black body is therefore given by E lambda t, which is equal to 2hc square by lambda raised to power 5 multiplied by e raised to power hc lambda kt minus 1. Now let's talk about some features of the spectral energy distribution. The monochromatic emissive power varies across the wavelength spectrum. The distribution is continuous but non-uniform. The emitted radiation is practically zero at zero wavelength. With increase in wavelength, the monochromatic emissive power increases and attains a certain maximum value. With further increase in wavelength, the emissive power drops again to almost zero value at infinite wavelength. At any wavelength, the magnitude of the emitted radiation increases with increasing temperature. The wavelength at which the monochromatic emissive power is maximum shift in the direction of shorter wavelength as the temperature increases. We can figure all these points out by looking at the graph shown previously in the presentation. Now let us illustrate the shifting peak nature of radiation with the diagram. In this diagram, we can clearly see that the radiation is a continuous function of wavelength. At a specified temperature, it increases with wavelength, reaches a peak, and then decreases with increasing wavelength. Radiation increases with temperature. Also, at higher temperatures, more radiation is at shorter wavelength. Moving on to the next law, we have Wien's displacement law. We know that at a given wavelength, the blackbody monochromatic emissive power increases with temperature. The wavelength, that is lambda max, at which there is a maximum decrease as the temperature increases. The wavelength at which the monochromatic emissive power is a maximum is found by setting the derivative of previous equation with respect to lambda, that is dE lambda t divided by derivative of lambda, that is d lambda is equal to derivative of 2hc square by lambda raised to power 5 into e raised to power hc by lambda kt minus 1 divided by derivative of lambda. From here we get lambda max into t must be equal to 2897.8 micrometer Kelvin or 2897.8 micrometer Kelvin. Also note that color is a function of absorption and reflection and not of emission. Now moving to the proper statement of Wien's displacement law. The product of absolute temperature and the wavelength at which the emissive power is maximum is constant and whose value is 2897.8 micrometer Kelvin. Wien's displacement law finds application in the prediction of a very high temperature through measurement of wavelength. Now let us see Wien's displacement law for 3 different stars. Here we compared Wien's law for 3 different stars, namely Spica, the Sun and Antares, with temperature 23,000 Kelvin, 5,800 Kelvin and 3,400 Kelvin respectively. Here we see that as the wavelength increases, the temperature decreases in order to make the product of wavelength and temperature a constant. Now this brings us to our final law, which is Kirchhoff's law. Now it states that for any arbitrary body emitting and absorbing thermal radiation in thermodynamic equilibrium, the emissivity is equal to the absorptivity of the body. That is, emissivity epsilon at a temperature T must be equal to absorptivity alpha at the same temperature T. Moving on, we have emissivity. Now what is emissivity? As we know, the ratio of the emissive power E to absorptivity alpha is same for all bodies and is equal to the emissive power of a black body at the same temperature. The ratio of the emissive power of a certain non-black body E to the emissive power of a black body EB, which is also the maximum emissive power, both being at the same temperature, is called the emissivity of the body. Now the emissivity of a body is a function of its physical and chemical properties and the state of its surface, which can be rough or smooth. Mathematically, emissivity epsilon is equal to E divided by EB or W divided by W black body, where E is the emissive power of a certain non-black body, whereas EB is the emissive power of a black body. Also, the emissivity epsilon relate to absorptivity alpha at thermal equilibrium according to Kirchhoff's law, that is, epsilon is equal to alpha, that is, emissivity is equal to absorptivity. Although this strictly applies at thermal equilibrium, we normally assume that it applies at all temperatures. Now Next we have emissive power. Now this emissive power of a black body is defined by STEFAN-BOLTZMANN law, which is W is equal to sigma T raised to power 4, where sigma, also known as STEFAN-BOLTZMANN constant, is equal to 5.676 into 10 raised to power minus 8 with units watt per meter square Kelvin raised to power 4. Now for a non-black object, that is an object which is not a perfect radiator, we can write the following expression: W is equal to epsilon sigma T raised to power 4. Moving on, we have heat transfer rate by radiation. Now for calculating heat transfer rate by radiation, one must include terms of energy received from surroundings and energy output. Now the energy input that we have is sigma alpha T infinity raised to power 4, where T infinity refers to the temperature of the surroundings, whereas energy output is epsilon sigma Ts raised to power 4. Now let us assume that epsilon is equal to alpha, and multiplying by area yields Q is equal to epsilon sigma A multiplied by the difference of the fourth power of Ts and T infinity, where Q is defined as the heat transfer rate and A is area. This above expression is for an object that is totally enclosed by surroundings at temperature T infinity. Now let's move to a very important topic, which is view factor. Now the factors on which the radiative heat exchange depends are absolute temperature of surfaces, radiative properties of surfaces, and the last one, geometry and relative orientation of the surfaces involved, that is quantified by what is known as view factor. Now let us define what a view factor is. So a view factor is defined as the fraction of radiant energy leaving one surface which strikes a second surface directly, where directly means that reflection or re-radiated energy is not considered. Now this view factor is denoted by F12, where the first subscript, that is 1, stands for the emitting surface, and the second subscript 2 stands for the receiving surface. Therefore we have F12, which is equal to direct radiation from surface 1 incident on surface 2 divided by total radiation from emitting surface 1. Let's derive a general relation for view factor between two surfaces. Let's start with infinitesimal areas. Now consider differential areas dA1 and dA2 on two black surfaces, namely A1 and A2, which are exchanging heat by radiation only. Now this schematic diagram shows us two black bodies which are interacting with each other through radiation and have areas A1 and A2 respectively. Now dA1 and dA2 are at a distance of r apart, and the normals of these areas make angles phi1 and phi2 with the line connecting them as shown in the figure. Then using the definition of intensity, we can write energy leaving dA1 and falling on dA2 equal to dQ1, which is equal to intensity of black body dA1 multiplied by projected area of dA1 on a plane perpendicular to line joining dA1 and dA2 multiplied by solid angle subtended by dA2 at dA1, that is dQ12 is equal to IB1 multiplied by dA1 cos phi1 multiplied by dA2 cos phi2 divided by r square. Now the total energy radiated from dA1 is given by dQ1, which is equal to EB1 multiplied by dA1. that is dq1 is equal to pi ib1 multiplied by da1. Then by definition, the view factor f da1 da2 is the ratio of dq12 to dq1, that is f da1 da2 is equal to cos phi 1 multiplied by cos phi 2 multiplied by da2 whole divided by pi r square. Note that the view factor involves geometrical quantities only. Now this equation gives the view factor between two infinitesimal areas. Such a situation is encountered even when finite areas are involved, when the distance between these two areas r is very large. Now for this, the infinitesimal areas must be converted to finite areas, that is the emitter is very small and the receiving surface is of finite size. Here integration over the entire surface E2 has to be considered. Again, remembering the definition of view factor and forming the ratio of dq12 to dq1, we have f da1 da2 is equal to integration ib1 multiplied by cos phi 1 multiplied by da1 multiplied by cos phi 2 multiplied by da2 divided by r square, and this whole term is divided by pi ib1 multiplied by da1. Since both ib1 and da1 are independent of integration, we can rewrite the equation as f da1 to a2 is equal to integration cos phi 1 multiplied by cos phi 2 multiplied by da2 divided by pi r square, and this integration is now only dependent on a2. Now this above or the previous case is for a small thermocouple bead located inside a pipe or a small spherical point source radiator located by the side of a wall, etc. Now considering the case of radiation from a finite to finite area, once again from the definition of view factor we have f a1 a2 which is equal to integration for a1 into integration for a2 of ib1 multiplied by cos phi 1 multiplied by da1 multiplied by cos phi 2 multiplied by da2 by r square, and this whole term is divided by integration for a1 of pi multiplied by ib1 da1. For constant ib1, the above equation can be rewritten as f a1 to a2 which is equal to 1 upon pi a1 integration for a1 multiplied by integration of for a2 of cos phi 1 multiplied by cos phi 2 by r square multiplied by da1 da2. In general, we can write this equation compactly as f12 which is equal to 1 upon pi a1 integration from 0 to a1 integration from 0 to a2 of cos phi 1 into cos phi 2 divided by r square multiplied by da1 da2. This forms our equation A. Here f12 means the view factor from surface 1 to surface 2. Similarly, the view factor from surface 2 to surface 1 can be found out as f21 which is equal to 1 upon pi a2 integration for a2 integration for a1 of cos phi 2 multiplied by cos phi 1 divided by r square multiplied by da2 into da1. This forms our equation B. Multiplying the equation A by A1 and equation B by A2 and equating double integrals, we get a simplified result which is A1 into F12 is equal to A2 into F21. Now this equation is known as reciprocity theorem and is a very useful and important relation. An important note is that it is easier to remember the view factor relation given in the equation A, which is A1 multiplied by F12 is equal to integration 0 to A1 integration 0 to A2 of cos phi 1 cos phi 2 divided by pi r square dA1 multiplied by dA2. Next, we have expression of view factor for some common geometries of finite size, namely aligned parallel rectangles, coaxial parallel discs, perpendicular rectangles with a common edge, and their view factor relation can be easily seen in this table as listed. Next, let us see some properties of view factor. Now, this view factor depends only on the geometrics of the bodies involved and not on their temperatures or surface properties. Also, between two surfaces that exchange energy by radiation, the mutual shape factor are governed by the reciprocity relation, that is A1 F12 is equal to A2 F21, which is area of surface 1 multiplied by view factor from surface 1 to surface 2 must be equal to area of surface 2 multiplied by view factor of surface 2 to surface 1. When a convex surface 1 is completely enclosed by another surface 2, it is clear from figure A, which we will see in the next slide, that all the radiant energy emitted by surface 1 is intercepted by the enclosing surface 2. Therefore, view factor of surface 1 with respect to surface 2 is equal to unity, that is F12 should be equal to 1, and the view factor of surface 2 with respect to surface 1 is then easily calculated by applying the reciprocity relation, that is A1 multiplied by 1 must be equal to A2 multiplied by F21, and from here F21 can be calculated as the ratio of A1 by A2. Now let us see view factors of a few surface. Now this first case is the one we discussed in the previous slide. Here the view factor from surface 1 to surface 2 is 1, and then we calculated view factor from surface 2 to surface 1 as the ratio of A1 and A2. In the second case, we have a flat surface and its view factor is 0. The next case is of convex surface, and here also the view factor must be equal to 0. Since the radiation do not interact with the surface again, in the last case we have a concave surface where we have the view factor which is not equal to 1, since some of the radiation can interact with the surface directly. Briefly, we can say radiation emitted from a flat surface will never fall directly on that surface again, as we can see in figure B, that is view factor of this flat surface with respect to itself must be equal to 0, that is F11 must be equal to 0. This is also valid for the convex surface too, as we have seen in figure C. But for a concave surface, it is clear from figure D that F11 is not equal to 0, since some fraction of radiation emitted by a concave surface does fall on the surface directly again. Now, if two plane surfaces A1 and A2 are parallel to each other and separated by a short distance between them, practically all the radiation issuing from surface 1 must fall directly on surface 2 and vice versa. Therefore, F12 must be equal to F21, which must be equal to 1. When the radiating surface 1 is divided into, say, two subareas A3 and A4 as shown in the next figure on the next slide, that is figure capital A, we will have A1 F12, which must be equal to the summation of A3 F32 and A4 F42, and it is obvious that F12 is not equal to the summation of F32 plus F42. Now let's see view factor for subdivided surfaces. Now, as discussed earlier, here is the figure capital A, from which we can conclude that A1 F12 must be equal to the summation of A3 F32 and A4 F42. We also have a second case as figure V, in which the receiving surface A2 is subdivided into A3 and A4, and we get the expression A1 F12 must be equal to A1 F13 plus A1 F14. That is, if the receiving surface A2 is subdivided into parts A3 and A4 as shown in the previous figure capital B, we will have A1 F12, which is equal to A1 F13 plus A1 F14. That is, F12 is equal to F13 plus F14, which was not true in the previous case of figure capital A. That is, view factor from the emitting surface 1 to a subdivided receiving surface is simply equal to the sum of the individual shape factors from the surface 1 to the respective part of the receiving surface. Now this rule is known as superposition rule. Next, moving on to the next rule, which is symmetry rule. Now if we have two or more surfaces which are symmetrically located with respect to the radiating surface 1, then the view factors from surface 1 to these symmetrically located surfaces are identical. A close inspection of the geometry will reveal if there is any symmetry in a given problem. Next, we have summation rule. Since radiation energy is emitted from a surface in all directions, then the conservation of energy principle requires that the sum of all the view factors from surface 1 to all the other surfaces forming the enclosure must be equal to 1. We will see figure capital C, where the interior surface of a completely enclosed space is subdivided into n parts, each of area A1, A2, A3 and so on up to An, as we can see in this diagram. Here we can write summation Fij starting from j is equal to 1, it must be equal to 1, and here I is equal to 1, 2, 3 up to n. Then we will have F11 plus F12 plus so on up to F1n must be equal to 1. Again F21 plus F22 plus so on up to F2n, that is also must be equal to 1. Continuing it to Fn1 plus Fn2 plus so on up to Fnn, which must also be equal to 1. That is, combining all these equations, we will get this expression as discussed previously in figure capital C. Moving on to our next topic, that is heat exchange between non-black bodies. The black bodies absorb the entire incident radiation, and this aspect makes the calculation procedure of heat exchange between black bodies rather very simple. That is, one has to only determine the shape factor. However, the real surfaces do not absorb the whole of the radiation, that is, a part is reflected back to the radiating surface. Other thing is, the absorptivity and emissivity are not uniform in all directions and for all wavelengths. Let us consider a case of infinite parallel planes. The assumption made in this are: number 1, surfaces are arranged at small distance from each other and are of equal areas, so that practically all radiation emitted by one surface fall on other. The shape factor of either surface is therefore unity. Number 2. Surfaces are diffuse and uniform in temperature, and that the reflected and emissive properties are constant over all the surfaces. Next, the surfaces are separated by a non-absorbing medium such as air. Next, let us see a schematic diagram of two infinite parallel planes. Here we have plane 1 and plane 2 having alpha 1 epsilon 1 T1 and alpha 2 epsilon 2 T2 respectively as their absorptivity, emissivity and temperatures. Here plane 1 emits radiation of power E1 to plane 2, but plane 2 only absorbs and emits a part of it, which is alpha 2 times E1, and the rest, which is 1 minus alpha 2 times E1, is reflected back to plane 1. Now this plane 1 emits only a part of the incident radiation, that is alpha 1 times 1 minus alpha 2 multiplied by E1, and reflects the rest of it, that is 1 minus alpha 1 times 1 minus alpha 2 E1. Now this reflected radiation is incident on plane 2 again, and again plane 2 only absorbs and emits only a part of it, which is alpha 2 times the incident radiation, and reflects the other part of it, and this process goes on forever. Now let's study heat transfer between these infinite parallel planes. Now the amount of radiant energy which left surface 1 per unit time is Q1, which is equal to E1 minus the sum of all the radiant energy which are again incident on the surface of the plane 1 after getting reflected from the surface of the plane 2, that is alpha 1 multiplied by 1 minus alpha 2 multiplied by E1 plus alpha 1 1 minus alpha 1 multiplied by 1 minus alpha 2 square multiplied by E1 plus alpha 1 1 minus alpha 1 square multiplied by 1 minus alpha 2 cube E1, and this series go on up to infinity. Now taking out alpha 1 1 minus alpha 2 E1 out of the bracketed terms, we are left with 1 plus 1 minus alpha 1 1 minus alpha 2 plus 1 minus alpha 1 square 1 minus alpha 2 square plus so on up to infinity. By simplifying all these terms and letting P equal to 1 minus alpha 1 into 1 minus alpha 2, we get this equation, which is E1 minus alpha 1 1 minus alpha 2 E1 multiplied by 1 plus P square plus P cube and so on up to infinity. Now this bracketed term, that is 1 plus P square plus P cube up to infinity, can be written as 1 upon 1 minus P, because P is less than unity. Putting this expression in the verb equation, we will get Q1 will be equal to E1 minus alpha 1 1 minus alpha 2 E1 divided by 1 minus P. Taking out E1 as common, we will get E1 multiplied by 1 minus alpha 1 multiplied by 1 minus alpha 2 divided by 1 minus alpha 1 into 1 minus alpha 2. This is done by putting back the value of P, that is 1 minus alpha 1 into 1 minus alpha 2. Now again solving it further, we will get E1 multiplied by alpha 2 divided by alpha 1 plus alpha 2 minus alpha 1 alpha 2, as alpha is equal to epsilon. From Kirchhoff's law, we can rewrite the equation as Q1 equal to E1 multiplied by epsilon 2 divided by epsilon 1 plus epsilon 2 minus epsilon 1 epsilon 2. Now for surface 2, similarly the amount of heat which leaves surface 2 can be calculated as Q2, which is equal to E2 multiplied by epsilon 1 divided by epsilon 1 plus epsilon 2 minus epsilon 1 epsilon 2. This can simply be done by changing 1 to 2's and 2 to 1's in the previous equation. Therefore, the net heat flow from surface 1 to surface 2 per unit time is given by Q12, which is equal to the difference of Q1 and Q2, which is equal to E1 epsilon 2 divided by epsilon 1 plus epsilon 2 minus epsilon 1 epsilon 2 minus E2 multiplied by epsilon 1 divided by epsilon 1 plus epsilon 2 minus epsilon 1 epsilon 2, which can be simplified to get the net heat flow from surface 1 to surface 2 per unit time, which is E1 into epsilon 2 minus E2 into epsilon 1 divided by epsilon 1 plus epsilon 2 minus epsilon 1 epsilon 2. Now Stefan-Boltzmann law for the non-black surfaces states that E1 is equal to epsilon 1 sigma T1 raised to power 4 and E2 is equal to epsilon 2 sigma T2 raised to power 4. Therefore Q12 is equal to epsilon 1 sigma T1 raised to power 4 epsilon 2 minus epsilon 2 sigma T2 raised to power 4 epsilon 1 whole divided by epsilon 1 plus epsilon 2 minus epsilon 1 epsilon 2. Solving this equation by taking out epsilon 1, epsilon 2 and sigma as common, we will get this expression, and from this expression we can substitute epsilon 1 epsilon 2 divided by epsilon 1 plus epsilon 2 minus epsilon 1 epsilon 2 as F12, where F12 is called as the interchange factor for radiation from surface 1 to surface 2 and is given by F12 is equal to epsilon 1 epsilon 2 divided by epsilon 1 plus epsilon 2 minus epsilon 1 epsilon 2. Simplifying it further by dividing numerator and denominator both by epsilon 1 epsilon 2, we will get this expression, which is a simplified form of interchange factor, that is 1 divided by 1 upon epsilon 1 plus 1 upon epsilon 2 minus 1. Lastly, we have some example of interchange factor as given in the table. We already did example 1 of infinite parallel planes, in which we calculated geometric factor as 1 and interchange factor as 1 upon 1 by epsilon 1 plus 1 by epsilon 2 minus 1. From this table we can also get the values of geometric factor and interchange factor of infinitely long concentric cylinders or concentric spheres and body 1, which is small, enclosed by body 2, also of body 1, which is large, enclosed by body 2, and last but not the least, two rectangles with common side at right angle to each other. And this brings end to our presentation. Thank you.